So my name is Susanne Kratzer and I'm visiting here Tartu Observatory this week. I'm visiting Krista Alikas. I've been working at Stockholm University for 25 years and I'm an associate professor there. And I've been working with the remote sensing of the Baltic Sea, mostly at Stockholm University, but also Lake Vänern, which is the biggest lake in the European Union. Before that, I did my PhD in Wales, in the United Kingdom, in Bangor, in the School of Ocean Sciences, and there I started learning about sea truthing and doing optical measurements of marine waters. And then I worked mostly in the Irish Sea and the North Sea, and I also had the opportunity to go to the Canary Islands, and we had a cruise there, and also in the Outer Hebrides on the shelf edge in Scotland. So but this talk is about remote sensing of and validation of waters that are rich in colored dissolved organic matter. And these waters are special from a marine point of view because most marine waters don't have so much terrestrial influence. So we usually have low CDOM, colored dissolved organic matter. But of course, if you look at lakes, it's a completely different picture because they're very much influenced often by colored dissolved organic matter and also by suspended particulate matter. So in this presentation, I will first show you some of our remote sensing research we've done at Stockholm University in the Baltic Sea. And then the second part is a more specific case study about Lake Vänern, where we have an AERONET-OC station. I will explain later a bit more about AERONET-OC. So the part one about the Baltic Sea. I will first show sort of, you can't do like in a lecture, full lecture of remote sensing of coastal waters, but I'll try and summarize what are the key components of the remote sensing in coastal waters and also how it is connected to ecology. And then important factors that are influencing the optical properties of the Baltic Sea. And then I'll show you some examples of satellite validation and algorithm development, and also some examples of where we had an optical mooring deployed, where we derive optical components from the mooring measurements, and then also some results of our remote sensing research in general at Stockholm University. So basically, I try to summarize it all in one figure. So I try to lead you through this figure. So we have a remote sensing imager in space, radiometer, and from this we can derive the spectral reflectance. And then of course we have to do atmospheric correction to get away the influence from the atmosphere. So we actually retrieve the information of the water leaving radiance. And then we can use radiative transfer modeling to derive A, which is the absorption coefficient, and B, which is the scattering coefficient. And from absorption, we can derive information about the absorption of colored dissolved organic matter. That's also used called unique substances. And also from the absorption at 442 nanometers, we can also derive chlorophyll A, or like an indicator, which is used as an indicator for algal biomass. From the scatter, we can derive information about suspended particulate matter and turbidity. They are related to one another, so the more particles you have in the water, the more turbidity you have, and also the more scatter, so they are all intercorrelated. And this gives us information about the sediment transport, especially in coastal waters. And the algal biomass, of course, gives information about the eutrophication status of the water body. And all of these three main optical components, they influence the Secchi depth and also the diffuse attenuation of light, the KD PAR. So that's the PAR is the photosynthetic active radiance. So that's basically the light that the plants can use, and this also then determines the growth depth macroalgae and also of seagrass. So often this growth depth is used also for an indicator of eutrophication, because if there's a high algal biomass, this reduces the Secchi depth, and then the algae, they start growing closer to the surface. And then, of course, we also have near-infrared information on our sensors, and from that we can derive sea surface temperature and get information about upwelling currents and more large-scale dynamics of the water body, and all of these influence, again, the optical properties. And there's also another connection to ecology. Basically, the turbidity can also influence fish behavior and the distribution of fish in the coastal waters, because some fish, they can hide better in turbid waters from predators. And the predators, they see it's clearer waters. So some fish species, they like to be in more turbid waters. So here you see sort of a results from the Ocean Color CCI project. And basically this is merged satellite data from various missions from NASA, the SeaWiFS and MODIS, and also from ESA's MERIS mission. And here you can see the changes of the months. And basically this is very precious information for oceanographer, because this is now that we actually can get almost a full coverage of the Earth. And you see here the typical distribution of chlorophyll. So we have these what are called the gyre, like the open ocean gyres. These are called the deserts of the oceans, because there's hardly any chlorophyll. There's too little nutrients in these water types. But then in the coast, of course, you have the influence here from upwelling. That's the African coast. We have a lot of upwelling on the western side of Africa. So you get a lot of nutrients coming in, and that stimulates the phytoplankton production. You also have here the coastal areas, and we have sometimes bad coverage. That's because we have often clouds in these regions. But also we have only a 4-kilometer resolution. So for some water bodies, of course, this is very low resolution. But apart from that, the absolute values are also not quite correct always in the coastal water types, because these algorithms that we're usually applying there for so-called case 1 waters, so optical case 1 waters are clear ocean waters. So if you apply these algorithms, they would be quite accurate in the open ocean, but the more you go into the coastal areas, the less accurate this data is. Although it's still valid, because you can see where the high productions are, but you can't really rely on the values. So this is what we've been trying to work, at least in the Baltic Sea, on to get these values more correct for the Baltic Sea. So we have several factors influencing the optical properties in the Baltic Sea. So first of all, we have a permanent salinity stratification in the whole Baltic Sea basin, which means that we have brackish water at the top and the more saline water at the bottom. And this gives quite a permanent stratification that can't be overthrown by wind, or would need a lot of energy to overthrow this. Then the surface layer is brackish, and it's the salinity is changing from about 33 in the Skagerrak region, and then when we go down to the Kattegat in the Danish Straits, it gets around 30 salinity units, and then the more you go north, the lower the salinity. And when you're up in the Bothnian Sea, at the very north of the Baltic Sea, we have salinities of only about 2. So that is almost freshwater environment. And that means that this is very tough. These are very tough conditions for plants to live in, or also for animals. So we have relatively poor species abundance in the Baltic compared to other oceans or seas. The major phytoplankton blooms that we have are in the spring. We have diatoms and dinoflagellate blooms. They make up the spring bloom. And in very specific for the Baltic Sea is that we have filamentous nitrogen-fixing cyanobacteria. You don't get these in other seas and oceans. So here's an example of a Sentinel-2A image that has about a 10-meter resolution, and here you see those the surface accumulations of cyanobacteria. They can like float on the surface because they have gas vacuums. Then, of course, we have also frequent upwelling in summer, and that can bring nutrient-rich bottom waters, and that can stimulate the production of these blooms because they have their internal, they have internal phosphate reservoirs, but they need nitrogen, and that can come with the upwelling, and then these blooms are triggered. So, but usually they only happen in warm water, so we would need quite also calm conditions and warm waters for these blooms to happen. And of course, generally eutrophication, so a high production of organic matter in the water column, makes the water quite murky, mostly due to algal growth. So these are quite complex optics in the Baltic, and it changes seasonally as well as geographically. Then here is an example of the reflectance spectra from different types of ocean waters or sea waters. So if you have very clear waters, you have the main reflectance in the blue. And then if you have high sediment, the reflectance is enhanced. And usually if you have high CDOM, then there's a high absorption in here in the blue. And then the reflectance, of course, is lower in the blue. In the Baltic Sea, we would be somewhere here. So we have a low reflectance. And we have the peak reflectance in the green, about 560 nanometers. And that's very typical for the Baltic. So the Baltic is very dark in comparison to the coastal areas where you have, or coastal waters where you have high sediment. The Baltic Sea has also relatively high sediment in the coastal waters, but it's like a range of maybe up to 20, turbidity of up to 20 FNU. But then you can, of course, have much higher ranges of turbidity. Some waters have up to 200 or 400. So the Baltic has relatively low turbidity and very high CDOM, so which means it's a very dark water body we're dealing with, which is very challenging, mostly for atmospheric correction. So we've been doing our work in different stages. At the beginning, we were very much focusing here. That's the Himmelfjärden area. We have a research station at ASKU at Stockholm University. So we did here, these are the transects we started visiting regularly. So this is through Himmelfjärden Bay. And then there's this transect out to BY31, which is Landsort Deep, which is the deepest part of the Baltic Sea. It's about 460 meters, I think. And then we have a transect here, because here we have an AERONET station that's run by JRC, the Joint Research Center in Italy. And then here we have an additional transect in Detsbro-Viken, this bay. And we added we started visiting this because we saw in the satellite images that there's high sediment and high reflectance. So we thought we should maybe visit this, or relatively high reflectance. And then in recent years, we have also had a lot of collaboration with Umeå University in the Gulf of Bothnia. And they do these regular monitoring trips, and sometimes we can join them when we have joint projects, and then we can also measure up there. Here we have very high CDOM waters, very low salinity. So we measure all sorts of optical properties. We measure with that's a radiometer that measures reflectance. It's a multi-channel instrument, so it's not hyperspectral. We measure Secchi depth with a water telescope to avoid the reflectance from the sea surface. We take water samples for chlorophyll, color dissolved organic matter, and for SPM and turbidity measurements. And then here we have a package where we have several optical instruments, and also a CTD to measure the sea surface temperature and the salinity. And then we have here something that's called a VSF meter that measures the volume scattering function. So we can define how the light is scattered spatially. And this is an AC9. That's a 9-channel instrument for absorption and attenuation measurements, from which we can both derive spectral absorption and spectral scattering, which is related to the reflectance of the sea surface. And then we have various other instruments. We added more instruments. So we have some turbidity meters, a sea point turbidity meter, and also a fluorometer with different channels that can also measure phycocyanin, phycocyanin. So we can look at also different types of phytoplankton pigments. So at the early beginnings, we started working with CWIFs, and then we could derive KD490, that's the diffuse attenuation at 490 nanometers. But then when I presented some of this work to end users, they said, but what's this KD490? We can't make sense of this. And then I got the idea that we could maybe relate this to Secchi depth. And so I derived an algorithm out from our data, so like a local algorithm, and then we applied this to the KD490 data, and then we could derive a Secchi depth map. So then the users were much more happy, because everybody has a concept, or everybody working with the sea knows what the Secchi depth is. It's basically you lower a disk in the water, and when it disappears, you note the depth, and that depth is the Secchi depth, and it tells you basically how clear the water is. So this is how then I thought, okay, we have now this KD for CWIFs, and then we had Maris that had different channels. So then I tried different band ratios from the remote sensing reflectance. Here this is 490, that's like the cyan band, against 620, that's one of the red-orange bands. And I found that this ratio gave the best correlation to KD490, corrected for the KD, the attenuation of the water itself. So then we could derive an algorithm for that, and then we applied that to Maris data. And then you see here that in the very inner base, we have very high KD values. That's because the attenuation is very high. And then the further you go out, the lower the attenuation, but then this is inversely correlated to the Secchi depth, so the clearer the water also gets then further out in the sea. Then here I wanted to show just an example of what this optical sensor that we've been using. It has a chain of sensors at 2, 4, 6, and 8 meters depth. So we measure the downwelling irradiance, ED, at these different depths, and from this we can derive the KD. All of them are at 400 nanometers. From that we can derive KD490. So we have moored this for a period of time in June, and then we could derive a time series. We had also a thermometer in this, so you can see here how the temperature changes over this deployment period. So this is the scale for the temperature here. And then we could derive the KD from the readings from our sensors there from this chain. And then I applied this local algorithm, and then could derive the Secchi depth. And basically it tells you several things, that the Secchi depth changes over time, and then if you have like a change in water masses, this can also influence the Secchi depth. So in most monitoring programs, people go out like a day and they visit several stations, and they take one Secchi reading at the station, but these are quite variable. So theoretically, one should go out more, measure more frequently. So this is the type of stuff you can derive with using radiometers in water. And then with many years ago, Krista and I started collaborating. And then we thought we could maybe improve the Secchi depth algorithms, and then we decided not to do like a simple band ratios only, but also include information about IOP, so the inherent optical properties. And we wrote a paper about this. And that's a more complex approach, and there we also use different band ratios that I couldn't use with my in-water instrument because it didn't cover like 710 nanometers, for example. But some of the ideas were based on the previous work we had done, and then here you can see like a time series from 2010, and that's like covering most of the Baltic Sea. And again, you can see here, like in the coastal region, you can see like coastal influence. And here these are the cyanobacteria blooms in summer. Sometimes they are higher in July, the coverage, and sometimes it's higher in August. It's completely weather dependent. And in September we get again autumn blooms, but these are usually not cyanobacteria. They're usually diatoms, but in recent years, because the summers have become warmer and the summers have been extending into autumn, then we sometimes can also still have cyanobacteria blooms. So remote sensing is a very good tool to look at these changes. Here's an example of an algorithm we derive for turbidity. Again, you can derive SPM from many of the ocean color processors that are like standard products. But many of the users don't have a concept of the ranges of suspended matter because they don't measure it themselves. But there are more and more labs that are measuring turbidity because it's important for the, not the Water Framework Directive, but the Marine Strategy Framework Directive, where you should you should measure turbidity in the coastal waters. So here we have applied our own algorithm to the SPM product, and then derived the turbidity product. And this is the northwestern Baltic, so that's our area where we have our research station on Askö. This is Himmelfjärden, and this is where we have like Landsort Deep, and we often get these cyanobacteria blooms there in the open sea. And this is in the southern Baltic. We have here the Bay of Gdansk and the Vistula Lagoon, and here we have the Curonian Lagoon in Lithuania. And here you can see that's the influence of the Curonian Lagoon. There's like a connection to the lagoon, and you have this point source here from the lagoon, where we have very high turbidities inside the lagoon, and it also affects the open sea. And here you can't see it, but the Vistula has some influence here that will be shown in some later images. Yeah, here. So here, this is Bråviken, that's like west of Himmelfjärden. Himmelfjärden would be somewhere here. So here you see in April, this is the effect of the spring bloom, and you see that it's sort of carried a little bit southwards, because we have in the Baltic Sea, we have this effect of the Coriolis force, means that the whole Baltic Sea is like turning anti-clockwise, the whole water body. So the rotation of the water would take the water down along the Swedish coast. So you see this a little bit here in this image. Yeah, and here you see that here the influence is changing over time, the coastal influence from the spring bloom, and then this is already some other type of bloom. Then in the southern Baltic, this is the Bay of Gdansk. Here we have the Vistula Bay, and here you see very clearly the point source of the Vistula River coming into the coastal area. Yeah, then over the years we have tested these different products, and we were then sort of quite happy with when we had got Mary's going and tested many algorithms. Then we got quite nice products, and they were all like quality controlled, and we could derive the uncertainties. So we could derive total suspended matter, chlorophyll, color, dissolved organic matter, Secchi depth, turbidity, and also we derived also inorganic suspended particulate matter from a local algorithm. But now we found that many of these products don't work as well with Sentinel-3. So currently, theoretically, Sentinel-3 should be almost identical to Maris, but somehow there are many challenges to actually get the products to the same quality. So the recent years we have been trying to work on this. So a recent paper I did with a PhD student, Sean O'Kane, he's from Dublin City, from Maynooth University, 30 kilometers of Dublin. And there we have now tested the level 2 water products in the northwestern Baltic Sea using the Case2 regional color CCC, Case2 regional CC algorithm, which is like it's like the standard algorithm they're using for optical Case2 waters. So basically for coastal waters or also for lake waters, you can use this. We also checked the vicarious calibration that EUMETSAT is using. This is an interesting thing because the system vicarious calibration has only been started. They have only started using this with the quite recently. I think in the Maris it was like with the latest Maris products, and then with Sentinel-3 it has been first applied to Sentinel-3A, and then only later to Sentinel-3B. But then these gains are applied. They are derived from the Moby station, which is in Hawaii, where we have very clear ocean water, so it's a very different optical water type. And basically in this paper we found that you can't really apply these vicarious adjustments to the Baltic Sea because it makes the products much worse. So there are very challenging things to work with in the Baltic because it's just a very different water type. And then we also assess the difference between the version 1 and version 2 of this, but this is very technical details, so I don't need to go too much into this. But we had a very large data set to test this because we had like some of the stations, these are the red ones, they are from my research, and then we had lots from the monitoring group. But these are also monitoring the red one. So there's also some of them are monitoring group. Then when you do the data quality control of all the pixels and stuff, then in the end, I think we started off with 3,500 pixels, but in the end we only had 128 matchups for chlorophyll. And then for the other properties, we had even less matchups because these are not measured so frequently, the other optical components. So what we found was that this version 2 with regionally adapted parameters, so we adapted adapted the salinity and the temperature for our region, and then we got a better fit of the values, we also found that these gains do not really benefit the level 2 water products in the Baltic Sea. And we found that this latest version of the Case2 regional CC overestimates suspended matter, total suspended matter, and even more than the first version of this. So you sort of think that the next version will work better, but it's not necessarily true. And then we found that there was actually some of the products were better estimated with the old version of this processor, and some were estimated better with the newer version. So it's also dependent on what type of parameter you're looking at, what type of processing chain you need to use. And this is, of course, very technical information, but for the end users, it's very important to know, is this data reliable? So we need to know this type of information. Yeah, we have also done quite some work in Lake Vänern. We've done several cruises there, and this was the most recent one where Krista and Ilma also joined, and also Alice Fabretto from CNR, who's Krista's PhD student. So we have this AERONET station here at Palgrunden Lighthouse. I don't know, in some of the photos later I can show you the station itself. And basically the aim was to intercompare radiometers, and we have here, this is the AERONET station, and this is Palgrunden Lighthouse, and this is the CML that is used for all AERONET stations, this type of instrument. It's a multi-channel instrument. And then here, this is the trial system that we hired from EUMETSAT, and Ilma had especially built this frame to deploy it. And this is the trial system from Tartu Observatory. It's placed on a slightly different frame. Ilma was testing different types of frames because, of course, the boats and ships, the sizes change, and so you need to avoid the shading from the ship. So Ilma is testing these type of deployments. And this is this radiometer, multispectral radiometer we have been using. This is also multispectral, but these are hyperspectral. Yeah, now I don't know how I'm doing with time, if I have time to show you this specific study in Vänern.
We have plenty of time.
Okay, basically we have now run the AERONET station in Lake Vänern for 18 years. Before we had it deployed in Gotland, so there's also a station Gotland, but that was initially based on the same instrument, and then we moved it first to SMHI, the Swedish Meteorological and Hydrological Institute, for 2 years. And there's also a station called SMHI, but neither Gotland nor SMHI are operational anymore, because ESA wanted us to have a station in Lake Vänern because it's the largest lake in the European Union. And at that time there were many lake projects, and they wanted that station. And I said I don't really have just money to move the station, but then they funded this initially, and later I got co-funding from the Research Council in Sweden, and then now it's funded currently by the Swedish Space Agency, this project. And we have all along collaborated with Giuseppe Sibordi. His group has been supporting us, but he's now working at NASA because he retired. So basically AERONET-OC is AERONET Ocean Color, is a sub-network of the NASA AERONET network. The radiometers measure the radiance emerging from the sea or from inland waters, so that we have some sites in lakes and as well as in the seas and oceans. And you can also derive the atmospheric properties. It's used for satellite validation of highest quality, and as far as I understand, currently there's no network that is comparable to this. The drawback is only that it's not hyperspectral. It has defined channels, but the data is very intercomparable between the different stations because they're calibrated in the same way. And the measurements comprise sky, sun, and water surface measurements. And it's measured at specific viewing angles, and they're all measuring in the same way. So this is like, these are all the AERONET station worldwide. There are more than 500, but these only measure the aerosol optical properties. And then this AERONET-OC does and additionally measure the water leaving radiance. So at the beginning, when we started our station, there were 9 stations worldwide, but this is growing. So now it's, I think, I have lost track, but around 38 somewhere stations. It might be 40 now. Yeah, it's based on the standardization of instruments, calibration, processing, and distribution of data. All calibrations, measurements and calculations are done using the same protocols and methods and providing site-independent data of high quality. We have annual pre- and post-calibration, which are performed at Goddard Space Flight Center of NASA, and all sun photometers in the network are intercalibrated against the same instrument from NASA. And then these normalized water-leaving radiances are provided on the web page. It's open to everybody, and you can get them at 3 data levels. Level 1 is the RAWS data quality, and it's provided in close real time. And then level 1.5 is almost real time, and includes an automatic data screening. So it's not affected by clouds or strong waves or superstructural perturbations. And then we have a final level, which is the so-called level 2, that's the best data level, and it implies the existence of pre- and post-field instrument calibration. So usually you only get them the year afterwards, because the instruments are usually, for us typically, it's been calibrated in winter, and then we only get the level 2 products in the beginning of the next year, basically. Yeah. And these are the GSAPC body has now written, they have implemented a code to do this automated data quality check. So I showed you already this, that is our AERONET site. Here, that's in the archipelago, and it's between the 2 basins here of Lake Vänern. And this is the latest version of the SIMAL instrument. It has here a peak. And that, can anybody guess why we have this spike here? Anybody worked with automated radiometric measurements? The birds. Because if you don't do that, your instrument will be completely white, and it will smell a lot. It smells anyway, but 1 year actually, when we tested this first, the spike was a bit loose, and apparently a bird was fell onto it and then flew away with the spike in its body. So it's also a bird killer. But we hope that it just keeps them, that this doesn't happen so often. It was a bit heartbreaking to find out. Sorry. I think that, okay. So this is the latest version of the SIMAL, and this has been deployed at Palgrunden since 2019. Before we had the older version of the instrument that had been in Gotland and at SMHI before as well. Then the important thing with this latest version is that the bands are actually matching OLG, so you don't need to do or before you had to do this band shifting to get the OLG matchups. And it also has more sensitive optics than the previous version of the instrument. And you can program a higher number of measurements, and that also helps to keep away the birds, because then this instrument it sort of shuts itself down, and then it starts awakening, and we take all these measurements, and that keeps the birds away because it's quite active. So then there were also many other improvements with the faster microprocessor and the larger memory. This is of course important if your GSM connection has problems, then you want to have a good large internal memory. And we have now built-in GPS. Before we didn't have this, so there were also always a problem with the accurate time and position determination, but it's at one point, so we know where it is. Then data transmission using GSM. This has been a headache last year because it had GSM3 built in, and in Sweden we are very progressive, and we're now moving on to GSM5, and we're going faster than most of the rest of Europe. And then the problem is that they're not continuing keeping up the GSM3 network, so they just let it continue, and then it will just stop working because it's not repaired or kept up. So we had problems with data coverage last year, and we weren't aware. We wondered, what's the problem? Why don't we get the data? but then we inquired and that discontinuing GSM-3. So now we're currently upgrading to GSM-4, and that will be operational a few more years at least. Yeah, that I had to tell you my frustration about this data coverage. And then we have also a better user interface, so it's more user-friendly to run. Yeah. So the relevance, the site has been operational since 2008, and it's one of the few high-latitude AERONET stations globally, and it's one of only 6 sites deployed in fresh water, and it was the first freshwater site, and it's deployed in a high CDOM environment. So Lake Vänern has about 1/meter CDOM attenuation at 440 nanometers. It's more than double as high than the open Baltic Sea, sort of an average. So it's quite high CDOM. And it contributes, our station contributes substantially to the validation of ocean color processes worldwide. Actually, I often get asked by people if they can use our data, and some of them invite me to their publications. So there's one example that was from 2021. We have here Palgrunden, and that's the freshwater site that has most of the data available for matchups. In this case, the matchup was using polymer for Sentinel-3 data. Yeah, so it's sort of nice to have this running, but it's a lot of work, and it's quite costly also to keep it going. So then in this case study I'm presenting at the moment, we have then also done some science on this, and basically this article was, the first author was Ilaria Casaniga from JRC. And here we used a combination of AERONET data and also data from the monitoring program in Sweden, the freshwater monitoring program, where you find data here. And here you have the absorption of CDOM from this database at SLU, the Swedish Agricultural University. And here you see the fluctuations in CDOM at 3 of the main monitoring sites there in the central lake. You can see that the CDOM was very high at this, and there was apparently a lot of pulp industry still that didn't do good water quality treatment, and that has improved, but you still get these fluctuations over time. Yeah, and then in this paper, then we also found that there are also fluctuations in the water-leaving reflectance. Here, this is the red reflectance, and this is the green reflectance, and you see, especially the red reflectance shows quite enhanced changes. And then, yeah, you can see the incremental changes over time here, 2008. I think it's actually 2009. And then we used satellite data to evaluate these changes. Ilaria was doing the data processing, but she used MODIS data because we had like a gap between the MERIS and the Sentinel-3 mission, so MODIS was a better option to get continuous data for a longer time series. Then what we first checked was data quality control of the MODIS data. So here this is the MODIS, the difference of the reflectance in the green against the reflectance in the red. This is green, yeah, it is green. Maybe it's already getting a bit orange or yellow. And then basically we saw quite good agreement at several spectral bands. Here's the example, is only for those. And the best agreement was shown by the green and to red reflectance difference. So this is interesting because you will find many papers where one uses reflectance ratios, but we also looked at the ratios, but they had a much higher variability. So then we found that if you use the difference of these wavelengths, then you get a much better match between the in situ and the satellite data. So here is the time series from 2003 through to 2021. So quite a nice time series from MODIS data, and I think it's quite an important data set because you can use remote sensing reflectance as an essential climate variable. So this will become more and more important for assessing the effect of climate change on water bodies. And you can see that the center wavelength shows periodical changes between 2003 and 2022, with clear minima occurring between 2010 and 2013. So here we have minima, and then you get again higher values. But we also observe quite strong differences between the two basins. So this is also where remote sensing is so important, because you can visualize the difference between the basins. And then we found significant correlations between the remote sensing reflectance in the red and turbidity. So this is the reflectance in the red, the whole thing. And also remote sensing reflectance and total phytoplankton biovolume. So this seems to be influenced by the phytoplankton production. So we have set up and sustained reliable reference measurements of remote sensing reflectance in Lake Vänern since 2008. The data has contributed to multiple studies of various ocean color processes and atmospheric correction models. The validated satellite products can be used to assess long-term trends in ocean color data, and remote sensing reflectance is an essential climate variable and was shown to be related to phytoplankton biovolume and turbidity in Lake Vänern. So I want to say we don't do research in a vacuum, and I've been working with all these people, and even many more in the last 25 years. And so I want to thank my students and also my colleagues and collaborators. And I just want to say that also for us it has been very important to have regular workshops, because that's really important for training the next generation of scientists, but also it's great for making new research contacts and getting to know the people you really want to work with. And yeah, that has led to many joint applications and some EU projects, and yeah, some really cool collaboration. So it's not just the teaching for the next generation, but also getting collaboration going. And of course, this also helps the students to build up their next networks if they get introduced into these such networks. This was examples from the Nordic network, which we had for 8 years. And yeah, maybe we can get something like this going again. I don't know. Would be fun. But yeah, thank you very much.
Thank you. So people who are in online can write their questions in the public chat, but people in the room would ask questions now.
So you have this case one thing, right?
Yeah.
And then you were saying already close to the shore, it's not always good, and it's maybe better to use this case two.
Yeah, usually we should use specific case two algorithms. My approach is actually you should have regional algorithms, but these are most of the times not available.
Which algorithms?
Regional.
Regional.
So like Krista and I, we have worked on some specific Baltic Sea algorithms where we also use the inherent optical properties, like for example, the scattering properties or the diffuse attenuation. And you basically need to adapt your algorithms to the water type you're working in. So it's actually quite complex, because these products from the CCI project, they look great, like on a global scale. It's really cool to see that. But scientifically, you can't really use that as yet, because the closer you get into the base and coastal areas, the less accurate this type of data is.
Is there some way how you can
tune it?
No, like I don't tune it, but like switch.
Yes, yes. I think Krista has also worked with combination algorithms, where you switch that, where you have certain thresholds, where you then switch to different band ratio algorithms dependent on water type. And there are now many approaches where you first derive the reflectance of the water type, and then based on that you then do a certain processing scale. Chain or certain algorithms that have been shown to work in this water type. Yeah. But it's all very dependent on the spectral shape of the reflectance. Yeah.
Miriam also has a question online. How often do you need to inspect the AERONET-OC instruments on site for potential issues caused by birds, weather conditions, or other factors?
Yeah, I think we do at least 3 times a year. We can monitor it because we have always access to the data on the AERONET-OC data. But the problem is that, of course, even if we see that there is a problem, sometimes we can't get a boat, or the person that runs the boat is not available, is on holiday, or the person who actually is my site manager is on holiday. So it's not always easy to actually directly respond to problems. So that's the main problem with the operation, that you would really need a huge team so that people are not on holiday all the time. Or no, I mean, people are not on holiday all the time, but that you can take turns and that you always have coverage. But our project isn't big enough, and we don't also have the funding to cover this type of. But I must say this new instrument has been very reliable. So we had only last year main problems because of the GSM-3, the gradual shutdown of the GSM-3 net. But since we have been using GSM, it has also become more affordable because it's much more expensive to send the data through satellite transmission. But then again, this type of data is just text files, so it's not huge amounts. But still, it's more expensive to use a satellite service.
But on these light towers, there is some space, dry space, where you could possibly store a hard disk or some flash memory, and you can have. You probably have.
Yeah, we have that. So, this instrumentation has we have a possibility to.
You have backup copy.
Yeah, we back up. If we lose the transmission data, we still have the data. So when we retrieve the instrument, we can download it. But then, of course, it's not like online because it's not being transmitted. But it's always a backup in case something goes wrong. So one winter, we had a real problem. It was like this. We were going to retrieve the station in August, and then my site manager, Niklas, got sick and he couldn't go. So we thought, oh, we do it in September. And then it was a very, very rough autumn, and it was so windy we couldn't access the lighthouse. And then it suddenly became winter, and it was a rough winter. Then it was suddenly all frozen, so we couldn't reach the lighthouse with a boat. And it was unsafe to go by some other means. I thought, oh God, I have destroyed the instrument because it doesn't have a heater. Some of them have heaters, so you can deploy them through winter, but we usually retrieve them in autumn. And then the problem was we couldn't do it, but I was worried. But then in February, it suddenly got quite mild, and then we were able to retrieve it. And so we could actually retrieve all the data, and the instrument was fine. The calibration values looked very good. And I was like, I really was lucky, I would say. You don't want to lose this type of instrument. It costs like 50,000 euros. So it's a big thing to destroy it. You take some risks with this type of research.
Miriam, there's thank you, and Alfredo is telling thank you for the presentation and giving a lot of appreciation for your work.
Thank you.
More questions?
One slide you were showing how you have used the national monitoring data in stations. So we are doing the same thing, that getting data from our national monitoring databases, and it's usually with very poor quality, or you have to spend a lot of time to do quality.
We have how we work with this.
Yes.
Yeah, we have actually had, I was funded by the Swedish Agency for Water, Marine and Water Management to do chlorophyll intercomparisons, and we've done lots over the last 5 years, and then I do workshops, and I also teach them optical measurements, so we all do comparable turbidity measurements. We use the same protocols for measuring CDOM. The problem is everybody does their own thing for chlorophyll. So some use the fluorometric method, some the spectrophotometric method, and then we started comparing those, and we found that they are within 20%, so it's not too bad. But now recently one group also changed to the fluorometric method, and now we are down to 10%, and that's really, for chlorophyll, it's a very low error. But it's a lot of work to get all the monitoring groups to actually participate in these courses, and to train their staff, and also to sort of learn that you should really use the same protocols. Everybody wants to keep doing their own thing. But now in recent years, we have managed to get people more interested. Yeah, we can maybe use a different type of, instead of, you can extract in ethanol instead of acetone, and then you have a lower variability. I think ULab is using ethanol, and that's actually very good, because it's much more exact. But ethanol overestimates the chlorophyll in comparison to acetone. And it's like the HELCOM protocols, they say you should use ethanol, but it can have an overestimation of up to 20%, which means then if everybody in the Baltic Sea uses ethanol, and internationally one uses a different protocol, it's 10% acetone, 90% acetone. So we actually have higher concentrations compared to the other countries, which is not good, because it looks like the chlorophyll values are higher in the Baltic than they actually are. So there are many things, and I think one needs to really put a lot of effort into comparing and doing joint workshops, and then show how one does the filtration, because we also found one lab was filtering too little volume, and that's why they got a higher error. So it's all very small details, it seems, but it's important to learn these things and to understand how you can reduce the errors of your own measurements. Actually, it was cool because I could use the way we do the error analysis of the satellite data against in situ data. Then I used this to define the errors between the different groups. So I could sort of transfer this knowledge, which was quite cool because nobody had done that in that monitoring program. So that was cool. But it's, one needs funding to do this, and maybe also try and get the monitoring agencies interested in that there is actually data quality problem, because most of the time people are very critical of the satellite data, and they say, oh, this doesn't work in the Baltic. But then you see that the in situ data has already its own problem, and there's so high errors between labs. So one should maybe work a little bit more with this, and also explain to this agency that actually in situ is not the answer either. Like you really need to work on it. The cool thing about the satellite data is it's consistent and it's based on physics. So it's really quite cool. But most people would rather criticize the satellite data because they don't have experience with it. Or
in one of the slides you also mentioned like seagrass.
yeah.
Is there a lot of seagrass in Baltic Sea?
Yes, we have.
And is it like uniform distribution or somewhere is more or less?
Yes, we have a lot at the west coast. So that's the Skagerrak and the Kattegat in the coastal areas. And then the more you go into the Baltic, the smaller they become. So we have eelgrass a lot. And then it stops at the Åland Sea. You know, Åland, this island. And then north of Åland, so in the Bosnian Gulf of Bosnia, there is no eelgrass. But further up, you have like other plants that would grow in the water, like normal plants. What is it? What do you call them? Vascular plants. Yeah, vascular plants. Yeah. So we have now a project where we look at underwater vegetation, but it's limited by the CDOM absorption. It's not so easy either if you do remote sensing on this. And then some people have started using drones as well in the coastal areas. But I think you have also some work at Tallinn or is it Tiit Kutsar's group he's in Tartu, is he? Tiit Kutsar.
They are both in Tallinn and Tartu.
Okay, yeah. They also do underwater vegetation.
Yeah.
And then you were mentioning the link between the turbidity and the fish species distribution. So are like, I don't know fishermen, but like people who study fish. So
there's some people that are interested in turbidity images or scenes because there was perch pike. I think it's one of the species that are quite dependent on turbidity. And some people prefer like to lay their eggs, or some fish, where it's turbid, so they can't be found, so that they thrive in this water type. So this can be interesting connection also to ecology, because often people sort of say, but what can you use this satellite data for? So that might be an interesting application also.
And then Secchi depth. Is it named after some?
Yes, Angelo Secchi. He was an advisor to the Pope in 1800 something. I forgot the date. And the Pope, I don't know what the Pope was called at the time, but he asked him to find a good method to evaluate the water quality in the Mediterranean Sea. So this is the oldest optical instrument we have. It's very simple, but there's a very long time series, and you can find time series all over the world. So, yeah, it's one of the few time series that are consistent. But they're not so consistent because it depends on how sensitive your eyes are. So it's not quite a physical measure.
I'm sorry, I don't know very well how the calibration of AERONET-OC is maintained. Do you send it to NASA for calibration every winter?
Yes, we do it like this at the moment. We send it to JRC first, and they do a lab calibration because Giuseppe doesn't rely on NASA. So then Giuseppe collects a number of instruments, but now Giuseppe is now at NASA. But Pietro, who's working in that lab in JRC, he sends them all the instruments to NASA, and then they all get intercalibrated against the same instrument from NASA. And then I think they found that there was some shift in the NASA instrument, and they only found it because Giuseppe does every time the calibration in his lab first. So he said that if he hadn't done that, they wouldn't have noticed that the whole network was shifting. So it's important to still do the lab calibrations and not to rely just on the intercalibration between equipment. And of course, you need also very, very good conditions for doing this intercalibration. I think they do it in Hawaii. It's a good excuse to go to Hawaii, I guess. On Mauna Loa, it's called, one of the clearest atmospheres in the world.
Siis that year when you had it for winter, for a longer time and it got a bit frozen, did it affect somehow for the calibration? Or?
No, this was, I actually checked the calibration values and they looked better than the year before. There was less drift. So I first thought, oh, I killed the thing. And then when I saw this, I thought, But I didn't have a good Christmas that year. I was a bit depressed about this instrument. I thought, oh no, I've spoiled it. It wasn't me, actually, it was the weather. But as a project leader, you're responsible, isn't it? It's terrible to feel like that. And then it wasn't a problem. Sometimes you can be lucky. But it's a lot of work, I guess you know, with how much work it is to take care of this equipment. And there's a lot of risks involved all the time, that it might get lost when it's being shipped somewhere or damaged or, yeah, all that.
More questions?
Good.
If not, then.
Thank you.